Integrated Math 2. This is lesson 1.03, and it's on a subject called dilations. What dilations are is it's simply taking a geometric shape. It could be a line, it could be a square, it could be a circle, it could be anything, and making it either bigger or smaller, but doing it proportionally. It's also distancing it proportionally from a fixed point called the center of dilation. So in other words, if you make the figure twice as big, if the figure is a certain distance from the center of dilation, and again, that's just a fixed point. The point could be inside the geometric figure or outside. It doesn't matter. But whatever that point is, if the geometric figure is a certain distance away from the center of dilation, and then you make the figure twice as big, then it should end up being twice as far away from the center of dilation. So that's what it simply means. So this is really not a hard process. What you're going to do is you're starting with a couple of points. So point A is at 2, 0. So let's review how you read a graph. You start at 0, 0, and the first number is how far you go along, is 0, 0. The first number is how far you go along the x-axis. It's how far you go horizontally. That means side to side. If it's positive, you go to the right. If it's negative, you go to the left. Then the second number is how far you go up and down on the y-axis. So in this case, it says 0, so you don't go up and down at all. So 2, 0 would be, from the starting point, would be 1, 2 to the right, and then it would be 0 up and down, so you would end up at that point right there. 2, 2 would be 2 to the right, positive 2, so it's 2 to the right, and then the second 2 means you go up 2, so 1, 2, so it's that point right there. Okay? And so what you're going to do is make this line, the K factor is how much you're going to multiply each of these numbers by. So in effect means you're going to make the line twice as long. You're also going to make it twice as far away from the center of dilation. Now, where's the center of dilation? It could be anywhere, but on all of the problems in this exercise, in this particular assignment, it's at 0, 0. It's right there at what's called the origin, the 0, 0 point. So let's go ahead and do this. And so what you're going to do is take each of these numbers and multiply it by 2. So that I'm putting a times 2 there for every one of these numbers. So 2 times 2 is 4. 2 times 0 is 0. 2 times 2 is 4, and 2 times 2 is 4. So this first point, 2, 0, moves to 4, 0. So 1, 2, 3, 4. There's a point. I'll make my dots really big so you can see them clearly. And the second one is going to be 4, 4. So 1, 2, 3, 4, and up 1, 2, 3, 4. Right there. And you should have a straight edge to do this, or something, piece of paper, card, something to do this. So the new line, the dilated line, that is the line that had its length or its shape change, you'll now notice it's twice as long as the original line. That's the K factor of 2. The other thing you'll notice is it's twice as far away from the center of dilation as the original line. The original line was 4. This one is, the original line rather was 2 on the x-axis. This one is 4. Also notice this, if you go diagonally, the top of the original line was 1, 2 diagonal squares, and this new line is 1, 2, 3, 4 diagonal squares. So everything got doubled when you did the dilation, where K, the dilation factor, equals 2. Okay, let's keep going. So it's the same thing here. So there are your two points. Those are the same 2 points as that. So verify that this is 2, 4, 1, 2, 1, 2, 3, 4. And this point over here, 1, 2, 3, 4, 5, 6, 1, 2. Okay, that's the original line. Now you're going to cut this in half. If they had you double this one, it would have gone off the scale here. So it's a good thing they didn't. So we're going to multiply everything here by 1/2. Okay, so 2 times 1/2 equals 1. Actually I can write it down here. So we're going to multiply 1/2 So 2 times 1/2 is 1, and 1/2 times 4 is 2. And then this is also going to be times 1/2. 1/2 times 6 is 3, and 1/2 times 2 is 1. So our new points, endpoints of the line are going to be this one, 1, 1, 2, and this one is 1, 2, 3, 1. So we'll draw that, and we'll check to see if it really did what it was supposed to do. Okay, first of all, the x-coordinate is half the distance, so this one is 1, whereas the original one was 2 right there, and the y-coordinate of this one is up 1, 2, and for this one it's up 1, 2, 3, 4, so everything got cut in half. Notice that the line goes down 2 and over 4. This line goes half of that, down 1 and over 2. Also notice that this point is 1 and 1, 2 up, and this point is 1, 2 and 1, 2, 3, 4 up. So everything in the new line got cut in half, and so I'm going to go ahead and write those coordinates there. 1, 2, and over here is 3, 1, and that's it. That's how you do that. Okay, let's keep going. Okay, on problem number 3, they want us to plot the original points, and then they want us to dilate that by 2. So we'll go ahead and plot the original points first. 1, 1. You can come over 1 and up 1. First thing you want to be sure is that your scale, that every square does equal 1. It doesn't have to. Now you see 2, 4, 6, 8, but that's because they number every second square, and that's just because it would be too crowded if they did 1, 2, 3, 4, 5, 6, 7, 8. So every square does represent 1 on the x-axis, and it also represents 1 on the y-axis. They don't have to be the same. They don't have to be 1, and they don't have to be the same as each other. So you need to watch out for that. So the first one was 1, 1, and the second one, B, is 3, 1. So we're going to go 1, 2, 3, and up 1, right there. So that's our original line. Okay, and we can label that. I have to write kind of small. Now we're going to double this. So we're going to multiply everything by 2. So that means I could have put that over here, times 2. So 2 times 1 is 2, 2 times 1 is 2. And then 2 times 3 is 6, and 2 times 1 is 2. Alright, so it's 1, 2, 1, 2, put that right there, and 6, 2. So 1, 2, 3, 4, 5, 6, and up 2. Okay, and there we are there. Draw that line. Okay, we noticed that everything doubled with the new line. This line had a length of 1, 2 squares, and this one is 1, 2, 3, 4 squares, so it doubled. This dot right here is one diagonal square up from the origin. That's the center of dilation. Again, is it 0, 0? You have to check that because it doesn't have to be there. So this one is one diagonal box. This one is 2 diagonal boxes, so that doubled. So everything doubled about the new line from the old line after dilation. Okay, let's keep going. This one's going to be 3/4, so you're going to get in a little fraction, some fractions here. Okay, so 4, 4, let's plot that. 1, 2, 3, 4, and 1, 2, 3, 4, right there. And 8, 12. And it doesn't give us enough graphs, so we're just going to kind of estimate 11, 12 right there. Okay, that should be 12, and I'll write it over here. That would be that dot right there. Okay, so that's our original line. It's going to look like this. Between those two, I kind of missed a little because I had my ruler upside down. Let's see if I can do a little better. Close enough. Okay, now we're gonna multiply everything by 3/4. So let's do that down here. 3/4 times 4. Remember, you can write 4 as 4 over 1. So remember, multiplication of fractions, 4's cancel, and you have 3 times, that becomes a 1. When they cancel, they become 1s. 3 times 1 is 3, and 1 times 1 is 1, so that equals 3. So that takes care of both of those right there. Now we have 3/4 times 8. And again, I'll put it over 1 so it turns it into a fraction. 4 goes into 4 once, 4 goes into 8 2 times. So that's 3 times 2 is 6, over 1 times 1 is 1, which equals 6. And finally we have 12 here. 3/4 times 12 over 1. 4 goes into 4 1 time, and 4 goes into 12 3 times. So 3 times 3 is 9, and 1 times 1 is 1, which equals 9. So let's go ahead and fill those in. The 4's turned into a 3's, 3 and 3. The 8 turned into a 6, and the 12 turned into a 9. Okay, so now we're going to plot that line. 1, 2, 3, 1, 2, 3 right there. And 6, 9. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So these two lines are really close to each other, and it didn't help that I didn't draw this line very well, so I want to try it again. Because they're right next to each other. It's a little bit odd to do that, but they did it. So here we have a point here, especially since we have to estimate where that 12 point was. We weren't really sure. So there's that, and now the other point was here. And those two lines should be parallel, but this line is 3/4 the distance of this line. So let's plot this. This was 4, 4 right here. And this was 8, 12. This was 3, 3. And this was 6, 9. Okay, it's a little hard to compare these, but we can look at one thing. This point right here, let's start with it. The original point was right here, is 1, 2, 3, 4 diagonal lines, diagonal squares rather, to get to this from the origin. So let me do that again. 1, 2, 3, 4. And this one is 3. 1, 2, 3 diagonal squares. So in other words, this distance is 3/4 as far as the original distance was. Okay, anyway, that's how you do that problem. And we'll move on. Okay, here we go. So we're going to multiply, we're going to plot these 2 points. So 0, 0 is right there at the origin. And negative 3, 2. Now we finally have a negative number. We're going to go to the left 3. 1, 2, 3, and up 2. 1, 2. So our original line is right there. And now we're going to multiply everything by 5. So 5 times 0 is 0, and 5 times 0 is 0. 5 times negative 3 is negative 15. And 5 times 2 is 10. Okay, so the first point on our new line, our A prime, that little tick means prime. It's called prime. It means it's related to A, and the B prime is related to B. Okay, so we've got 0, 0, and negative 15, 10. Oh boy, they didn't do us any favors here because we don't go to negative 15, so I'm going to guess. 1, 2, 3, 4, 5. I'm going to say it's about that far. If I wanted to be a little more precise, I could measure it with a ruler. And then we're going to go up 10, and this is exactly 10, so I'm going to try to make it even with this right here. Like that. Whoops, and I'm sorry, I should not have put a point there. That's just the negative 15, and then we had to go up 10, so it's here. So there we go. From 0, 0 to negative 15, 10 is going to look like this. Okay, and that's something like what they look like. So they actually should be on the same, going through the same point, but that's because I had to guess here. So if you look at this, well, anyway, these two lines. So this line, if you were to measure it, the shorter line is 1/5 the length of the longer line. Or put another way, the longer line is 5 times the length of the shorter line. I'm not going to measure that to prove it. It's true. All right, let's keep going. Now we're getting two-dimensional figures, not just lines. So determine whether the dilation from figure A to B is an enlargement or a reduction with the center of dilation at 0, 0. Then find the scale factor. Well, it's pretty obvious. You don't even have to take math class to see that B is smaller than A. So it's a reduction. Now what do you do to find the dilation? You find 2 points that correspond to each other, that are on the small triangle and the big triangle, that are right where grid lines intersect. These lines here are called grid lines. So for example, this one, we'll start at 0, 0, we go up 1. So the coordinate of this is 0 on the x-axis. You didn't move any direction that way, but you went up 1 on the y-axis. So that's 0, 1. Now that's right on a grid line, so we can see clearly that's 0, 1. Now what about this point? This is the corresponding. Corresponding means it matches up with it. This is a corresponding point with this. And what's the coordinate of that? 1, 2, 3. So it's 0 on the x-axis and 3 up. So this is going to be 0, 3. So with that one set of points right there, we can see that the bigger one is 3 times larger than the smaller one. Or remember, we were starting with A and going to B. So you would say that B, the scaling factor K, is 1/3. You started with the big triangle and you scaled down to the smaller triangle. So you had to multiply 3 by 1/3 to get 1. 0 times 1/3 is 0, that's fine. 3 times 1/3 is 1. So that's your scaling factor, is 1/3. Is there another point we could compare? Sure, we could compare this point right here. So that's down -1. So it's 0 on the x-axis again, and -1. You went down on the y-axis. This point, which corresponds right there, it's right in the center of the triangles, so they correspond. This one is 0, -3. So again, if you're going from this bigger triangle to the smaller one, you'd multiply this by 1/3. And 1/3 times this would give you 0, -1. 1/3 times 0, -3 would give you 0, -1. So the scaling factor is. Now, a tougher one to identify. Well, it's not tougher to identify. Let's go diagonally here. If we go from here, the center, to this corner of this triangle, it's diagonally 1, 2, 3 diagonal squares. You have to go 3 squares diagonally. For this one, you just have to go 1 square diagonally. So this one is 1/3 of this point right here. So every point is 1/3 of another point. This one's a little harder to tell because it's not right on grid line, but let's see, it looks like about 1/2. So that means this one ought to be 3 times as far, and that's 1.5. 1/2, 1.5. So 1.5 times 1/3 would give you 1/2 right there. But it's easier to pick corners that are on grid lines. That's the easiest way to do this. So we said it's reduced. It was asking us reduced. It was a reduction to go from A to B. And the scaling factor was 1/3. Okay, let's try this one. Okay, determine whether the dilation from figure A to figure B is an enlargement or a reduction. And with a center of dilation at 0, then find the scaling factor. So clearly going from A, this triangle, to B, this triangle, is an enlargement. So we can write that down. Okay. Now, again, do the same thing. Here's the center of dilation. It's the origin, 0, 0. It says that right there. Again, it doesn't have to be at 0, 0. They just made all of these problems so that it is. So let's look at this. A, if you look at this point right here, this corner of the triangle, it's 1, 2 squares away. If you look at this one, it's 1, 2, 3, 4, 5 squares away. So that means the center of dilation is 5/2. You can call it 2.5, but it's 5/2. We can look at this one as well. So this is 1, 2 if you go up the y-axis, and this one is 1, 2, 3, 4, 5. So you multiply this by 5/2. Let me just prove that. This is 0, 2. And this is 0, 5. If I take 0, 2, and multiply it by 5/2, well, 5/2 times 0 is 0. And 5/2 times 2, again, you can put a 1 underneath it to make it a fraction. The 2's cancel, equals 5. So that would be 5, and that's that point right there. Okay, so you have to enlarge it by a scaling factor of 5/2, which is the same as 2.5. All right, let's keep going. Okay, dilate the figure by the given factor. By the given factor, center of dilation is 0, so the factor is 2. So we have to identify each of the points first and write them right there. So let's start with A. A is 1 to the right, that's on the x-axis, and 1 up, that's on the y-axis. So it's 1, 1. B is 2 to the right and 1 down. So that's +2, -1. It goes down 1. And C, I think it's supposed to be right on that, is 1, 2 to the left. So that means the x-coordinate is -2. And once you're there, you don't go up or down at all. So that makes this 0. All right, so we're just going to multiply all this by 2. 2 times 1 is 2. 2 times 1 is 2. 2 times 2 is 4. 2 times -1 is -2. 2 times -2 is -4. And 2 times 0 is 0. Boom. There you go. Okay? So now you plot that. So A prime is 2, 2. So 1, 2, 1, 2. It's right there. Draw a big dot. B prime is 4, -2. So it's 1, 2, 3, 4, 1, 2. Okay. And finally, C prime is -4, 0. So you're going to go backwards. 1, 2, 3, 4. And you don't go up or down because it's 0. So now we're ready to connect our dots. There we go. And you can see it's pretty much a perfect fit. So what can we compare here just to verify that? Well, again, you have 1, 2 backwards, and for the original, and then 1, 2, 3, 4 backwards for the new one. That's multiplying by 2. Here you have, it looks like 1.5 right there. It's halfway between 1 and 2. So you multiply that by 2. You multiply 1.5 by 2, and you get 3. So 1, 2, 3. That's that point right there. So that point is twice that point. If we go diagonally in this direction, we go 1 diagonal square to get to our original, and we go 1, 2 diagonal squares to get to our new one. So that's a correct dilation. You expanded it, you enlarged it, and you doubled everything. Okay, we'll keep going. All right, so same thing. So I tell you what, I'm going to leave this to be a U problem. You need to plot each of these points, and then your dilation factor is going to be 1/4. So all the points you get, you're going to have to multiply all those numbers by 1/4 to come up with these, and then plot it. This is the only one I'm going to leave for you to do. It is a fraction, but you can handle a fraction. Okay, I'll go down and do this one. Again, if you don't know how to do number 9, if you come to tutoring, I'll answer any question, even the ones I don't do on the video. I'll answer any question. Okay, but you have to come to tutoring if you want to find out 9 and don't know how to do it. I think you should know how to do it, but if you don't, that's okay. Alright, so let's go ahead and plot these points. Now we have a four-sided figure. That doesn't matter. So A is 1, 2 to the right, and you don't go up or down, so that's 2, 0. B, you don't go right or left, you just go straight down 2, so that's 0, negative 2. C, you go backwards 2 and up 1, so that's negative 2, 1. And D, you go forwards 1 and up 1, 2, so that's positive 1, positive 2. This is a 1.5. Now you need to convert a mixed fraction into a. You can't do math with mixed fractions. So the way you do is you take the mixed fraction, and I call it around the world. You take the 2 times, that's a times sign. It looks like a plus sign. So let me try to make it look like a times sign. 2 times 1, and then you take the 1 and you add it. That is a plus sign right there. You add it to the 1 there, and then you put them all over that number right there. So if we do that, 2 times 1 is 2, plus 1 is 3, and you put the 3 over the 2, so that equals 3 halves. You can't do math with a mixed fraction. You have to be in an improper fraction like that. In other words, not mixed like that, to be able to do math. So that means everything here is going to be multiplied by 3 halves. Okay, so 3 halves times 2. Let's come down and do the math. 3 halves. I'm doing this first one right here. Times 2. You put a 1 underneath it to make it a fraction. The 2's cancel, and you end up with 3 over 1 is 3. So this becomes a 3. 3 halves times 0 is 0. 3 halves times this 0 is 0. 3 halves times negative 2, it's the same as this one right here, except it's a negative sign on it. So it becomes a negative 3. 3 halves times negative 2, same thing, is going to be negative 3. 3 halves times 1 is 3 halves, or 1.5. 3 halves times 1 is 3 halves. 3 halves times 2, we did that up here already, and that's going to be 3. Okay. Alright, so now we plot. So first one is 3, 0, 1, 2, 3, and 0, it's right there. I'll make a big dot. The next one is 0, negative 3, so we don't move anywhere this way, but we go down 1, 2, 3, right there. I'm going to make a big dot. Then negative 3, 3 halves, which is 1.5. So we're going to go backwards 1, 2, 3, and then it's positive 3 halves, so we're going to go up 1.5. It's right there. So I'm going to make a big dot right in between on this line and in between these two lines. Okay, and finally 3 halves 3. So that's 1.5. So we're going to go forward 1.5. That's right there. And then we're going to go up 3. 1, 2, 3, right there. So it's right on this line, but it's in between those two lines right there. And now we're going to do dot to dot. And there you see the two figures look exactly the same shape. It's just that the new one is 3 halves, or 1.5 times the smaller one. Again, let's start here and let's look at let's go diagonal squares. So this one is, well, that's not a good one. This one we already did. So this one is 1, 2, and the new one is 1, 2, 3. So that's 3 halves, or 1.5 times that. Same with this one. Again, every point is going to be 1.5 times from the old square to the new square, 1.5 times, and every point is going to be 1.5 times the distance that the old square was from the origin. So it makes it also 3 halves the distance away from the origin, from 0, 0. Okay, that takes care of this lesson. And it is 1.0. I think it's labeled wrong on here. Let me see. It's 1.03. It says 1.01 on the top of the page, but it's 1.03, okay? So that takes care of that lesson. We'll see you on the next lesson.